Hi there. Hope those other two examples went well enough. Maybe you'll have some questions for me when you get around to looking at them. Um, the next example I want to show you is sort of one that I hinted at and kind of promised along the way, which was how that equation we have for the distance covered over the course of an acceleration works even as motion reverses due to a continuing acceleration opposite to our original direction of travel. Slow down, slow down, slow down, get to a stop. If I keep accelerating in that reverse direction and begin reversing, um, we want to see how that equation just handles that in stride with no need for any additional work. So we're going to spend a little time with this problem. A jet lands traveling 60 meters per second and uses full reverse thrust and nothing else to arrest its forward motion. The resulting acceleration is minus 6 meters per second squared. The pilots leave the reverse thrust on after stopping, and the jet accelerates in reverse, same as before. The same acceleration. Because indeed it's the same engines running in reverse, it's the same thing. Questions we are asking: how long to stop and how far? Similar questions that we answered last time on the stopping distance problem. How far 2 seconds before the stop, 1 second, and how far 2 seconds after the stop? These are to investigate the behavior of distance traveled under acceleration. Let's begin with the easier questions that we've looked at before. How long to stop, meaning how much time? Well, we have to shed 60 meters per second, and we're losing 6 meters per second each second. So I will skip working this out and say that the time is 10 seconds, and you should be able to convince yourself that that is correct. It's 60 divided by 6. Now we want to know how far. What is the stopping distance? We do as before. D equals VIT plus 1/2 AT squared. Okay. Substituting in, we have initial velocity is 60. Time we said is 10 seconds because we are evaluating at the stop. Plus 1/2. Acceleration comes negative because it is opposing our motion direction. Minus 6 meters per second squared. And then we need to multiply by time squared, which is 10 seconds squared. And this comes to 300 meters. And make sure you can follow along on the calculator. So 300 meters down the runway, the aircraft comes to a stop. That takes 10 seconds. Now, we want to ask the question, what about 2 seconds before the stop? Just to poke around, we're just getting a sense. So 2 seconds before the stop would be at 8 seconds because it's 10 seconds to stop, 2 seconds before. So 2 seconds before, we're going to have D equals, now we have all the same numbers, but we have 60 meters per second. Now we have 8 seconds plus 1/2. Acceleration is the same. We're talking about the same acceleration, the same event after all. 8 seconds goes here, squared. And that comes to 288 meters. We can do a sanity check that this is less. Certainly we expect that. We expect to have gone not as far down the runway in 8 seconds as 10 seconds, so good. What about just down to 1 second before stop? So we solve again, and I'll drop the units just to go quick. So this is going to be solved at 9 seconds. That gives us 297 meters, again less than 300 as we expect. Something to point out here is this entire deceleration is 10 seconds long. After 9 seconds, there's 1 second left, or 10% of the time remaining. But if you notice, we've eaten up 297 meters. We have 3 meters out of 300 remaining. So with 10% of the time remaining, we have only 1% of the distance remaining. And this makes some sense. The beginning of your deceleration, you eat up the vast majority of the distance involved because you're going faster during those seconds. Now let's look at 2 seconds after the stop. Now recall that the acceleration continues. The thrust reversers are left on and begins pushing the jet backwards. Well, indeed, it's been pushing the jet backwards the whole time. That's what bled off all the speed, but is now going to cause a motion in the reverse direction, back up the runway whence it came. 2 seconds after the stop. Now, there's 2 ways you can do this. You could start essentially a new analysis where we say, okay, VI, initial velocity, is 0 because I'm now at a stop. I'm accelerating. I can rewrite and I can rearrange, in fact, my positive direction to be back up the runway whence I came. And t equals 2 seconds, right? A 2-second acceleration, and you'll get your answer. Which I think will come, you would see 12 meters. But if you want to, you don't have to do that. If you could simply be asked, what is the displacement of the aircraft after any time t? As long as this acceleration remains constant over the period, you can just plug in. You don't have to restart anywhere. You can you can start way from the beginning where we had that initial velocity of 60 meters per second. So let's do it. 2 seconds after the stop is 12 seconds after we touched down with initial velocity 60 meters per second. So we have d, and now it becomes kind of key to write this as the displacement, a clear position vector. Initial velocity is still 60 meters per second. Now we're interested in 12 seconds later minus 1/2 times -6 meters per second squared times 12 seconds squared. That's the t squared. And that comes to 288 meters. What does this mean? This is saying that 2 seconds before the stop, you are at 288 meters down the runway from your touchdown point. 1 second before the stop, you're at 297 meters. At the stop, you're at 300 meters. 2 seconds after the stop, you are back at 288 meters. Just like that, this equation handled the turnaround, the reversal of the direction of the aircraft. Indeed, you begin reversing direction. Another way to say that is your displacement from your touchdown point, or from the start of analysis. Your reversal begins when this term exceeds am I saying that right? Getting tired here. No, I did not say that right. Ignore that. Yeah, ignore that part. I'll make a better comment on that another time. But do notice the symmetry of this, that 2 seconds before the stop, we're at one position. 2 seconds after the stop, at a constant acceleration, we're back at the same position. And that's because, if you remember, our motion under constant acceleration, our displacement specifically, is that parabola shape. So here we start here. This is time. And the plot would look like this. It's a parabola. It comes from the t-squared term. We get this parabolic shape we saw a week or two ago. Now, we reach a stop. Now the stop is here where the slope is 0 at t equals 10 seconds. And you'll notice that equal units of time on either side correspond to the same displacement, just like we found here. And that's just a property of parabolas, is they are symmetric, like this. Anyway, I'll see you back for another one. Hope it makes some sense.